Over.
Okay, so maybe we can start the lecture. So let's continue. So with regular expressions, actually lecture 10. Today we will see the what do you call the object that is needed in the algorithm for checking whether a string contains a pattern given by a regular expression. Okay, so you remember we had two things in mind. One was what were regular expressions, and one was an algorithm that, given a string, checks whether a pattern is present. Okay, so for that we will study this object called deterministic finite automata. So here is the reference. So let's go to the. So let's first finish the exercises on regular expressions that we did. Okay. So these were the three things. Write regular expressions for the following. The first. So the first two things we already have seen. So the other thing was words that contain even number of A's. Okay, so even number could be 0 or a multiple of 2. So that I have written here. B star is even number of, 0 A's, and a non-zero even number. This is an expression for it. So the idea is that if I look at a word which has even number of A's, I first get the first context. So there will be, this will be full of B's, this will be full of B's, right? So here I make the first cut. Then I find the next two A's. There'll be an A here, there'll be an A here, and there'll be some B's in between. And then I make a cut here, and so on, until I get to the last two A's. Okay. and then once again there will be some b's here, and there will be an additional b on the right, padded on the right. Okay, so that's why we have this b star a b star a b star, the whole star. Okay.
Sir,
Yeah.
for 3.2 we did in the last class, should we have considered the epsilon because words with even length also include zero
Yeah, yeah.
words of zero length?
Yes. So we do that? So
We simply did a plus b the whole star.
no. We did this. What was the thing? No, what was the sigma? Okay. Sigma dot sigma star. No, that's fine, right? A plus b dot a plus b. This whole thing star, right? So the star makes sure that epsilon is already there. Do you get it? So then we don't need this. I agree with you. Okay. So was that the question?
Yeah, I get it now.
Yeah. Okay. So then we separately don't. No. Sorry. See, this is not added for epsilon. This is added for string containing 0 b's. See, this will give me epsilon, fine. But what about BB? Right?
Okay, huh.
So for that, I need this.
Got it.
Yeah? Okay, good. Okay. Any other questions? No? Okay, good. So then what was the next thing? There was an example 4. Write the language corresponding to the following expressions. So this AB plus C, this is the union. So there is an AB and an epsilon. It contains two strings, the string AB and this empty string. Okay, the epsilon string. Okay, AB plus empty set. This is AB union empty set. So it contains only AB. So this is to show you the difference between this one and this one. Epsilon is a singleton set containing a string epsilon. This is denoting just the empty set. Okay. Now A dot E is like I have A and then I do concatenate it with the set epsilon. So I take a word here, I take a word here, I do A dot E and then I'll just get A. Okay. Whereas A dot phi will be empty because I have to take a string here and this empty, there is no string here. Okay. So there is A dot no string should just give me no string. Okay. So A dot phi, because there's no string here. According to the definition, L1 dot L2 is you take a string W1 dot W2 such that W1 is in L1, W2 is in L2. Okay, you cannot find any W2 at all. So this is empty. Now what about this? This A dot B plus epsilon dot B. So this is AB and B. Okay, and finally, what is phi star? See, any language star is L power 0 union L power 1 union L power 2 and so on, right? What is L power 0? You don't take any string in the language. You just you take no strings in the language and then this gives me epsilon. It's the string of length 0. Okay. This will be you take all strings of L once. This will be you take strings of length, strings in L concatenated with strings in L and so on. So it doesn't really matter what that L is, even if it's the empty set. Okay, 5 power 0 will have epsilon. Okay, this is a technicality. Don't really have to worry about it. Okay,
Sir,
yes.
sir, in 4.3, can it be A epsilon?
Yeah, A epsilon is just A.
Okay.
Yeah, it's another notation for A. I mean, okay. Any other question? Okay, good. So let's get into finite automata. Okay. So, so yeah, as I said, what is the application? The application is they can be used as means for giving an algorithm to search for a pattern matching a given regular expression in a string. Okay. So we will see later how, but for the moment we need to understand what finite automata are. Okay, so let's give some context. See, we started with some kind of an alphabet. Okay, for now we have fixed the alphabet to be just A comma B, and we defined this notion called a language, which is, see, which is a subset of sigma star. You remember sigma star is the set of all words over A comma B. Okay, a language is some subset of sigma star. Okay, and these regular expressions can be used to describe certain languages in a finite notation. Okay, it's a way to succinctly represent a set of words. Finite automata are going to be yet another formalism to represent a set of words in a finite way. Okay, let's see how. So what we will do, before I tell what finite automata are, so I'll post this picture. This is my picture. Okay, so this AB is the regular expression, and for this language, this is the finite. So DFA stands for deterministic finite automaton. Just let's call it an automaton for today. Here is the automaton for it. For this language, here is the automaton. For this language, here is the automaton. Just read this, study this, and try to make an association why this picture should represent this picture should represent this, what are the various aspects in this picture, and so on. So I'll give you like some 4 minutes. It's 3:41, so I'll resume at 3:45. Okay, if you have not seen finite automata before, so please do this exercise of just trying to understand this association. Okay, why should this be this? So I'll resume again in a couple of minutes. Okay, so anyone, any answers? Of course, if you have seen automata before, please don't answer. But if not, any guesses why? So, what is this picture doing? What are the various aspects in this picture? And like, why do you think, why do you think this stands for this? so on. So anyone?
The double circle probably represents the end of the language.
Okay.
And so, for example, in the second, after A, there are two options. You can take A or B, but
Ah,
the language ends there.
correct.
Either there are two ways you can start with A or either with B.
Uh-huh.
And then after B, you have to take A, and then again the language ends.
Correct.
And in A star, the second uh,
Uh,
after or that you have given, that
uh,
simply means that you can go about taking and you end it with an and it there and then.
yes, yes, correct. So either you start from here, you
Or
either read an A or you just keep reading some number of A's. Yeah,
yeah.
correct.
And similarly for AB star, the second one is signifying you start from A, then go B.
Yeah.
You definitely will have to go through B,
Huh.
but you end there and you can go as many times as you want.
Correct. Yeah. So this is, thank you. Thank you. That Anukriti, is it? Yeah.
Yeah, yeah.
Thank you. Yeah. Thank
Anukriti.
you. So yes, indeed, this is roughly the idea. So this picture is quite intuitive as it is. So if I look at A star, so let me draw this. So let me look at A star. Okay, and let me take the smaller automaton, A. Why is this representing and how is it representing? See, what does A star stand for? It is the language given by epsilon, A, and so on, right? So both these pictures stand for this language. Okay, so this one we saw why. It's like kind of it's like defined in that way. Okay, so here you should think of it as, see, this is some kind of a machine which first takes some word, okay, and starts reading that word from left to right. For example, say it takes A. There is A. Okay, so call this state. Okay, I so call this circle some Q. Okay, so it's the machine is at Q. It reads A, and then it comes back to Q. Once again, it reads A, comes back to Q, reads A, and comes back to Q. And finally, as it was pointed out, you end in this circle is called a state. Okay, so you end in a state which is a double circle, which means you can accept this word. Okay, now suppose I take BAA. Let's just take BA. Now starting from here, there is no way to read the B. Okay, so this automaton rejects this BA. It accepts AAA, but it rejects BA. Now if you look at any word in this language, either A or AA or AAA or so on, any A power I, there is a way to accept it. By, you start from here, you keep reading that many number of A's, and you end in an accept state. Okay?
Sir,
Yes. Yeah.
how is this epsilon incorporated in this logic?
Yeah. So since this, okay. See, why did I start from here? So that was this arrow. So you should see that there are several things in this picture. So there are these circles. Some of the circles are double circles. Okay. And then there is this arrow here. This is signifying that it's a starting position. Okay. Now the starting position itself is an accepting position. Okay. It's an accepting state. So you don't have to read any, like, if that is the case, we say that epsilon is an accepting state. Epsilon is accepted. Okay, so I'll give you the formal definitions later, but if my initial position itself is accepting, then I also include epsilon in the language of this automaton. Okay, see, I'm throwing many words. Okay, but just try to get an intuitive understanding, but I'll give you a formal definition later. Okay.
Sir,
Ah,
then if in this diagram, if the left arrow is not there, which is pointing to the automata,
no,
so
you need to have a left arrow because you need to know where to start. In this case, there was only one state.
yeah, let's just assume that it's not there. So
Wait,
in
which
that
one?
case, right?
This arrow. Oh, if it's not there, then the language will be empty
Okay.
because you have to start from the position which is pointed by the arrow. I mean, you need to have the arrow.
Okay. Okay. Okay.
Okay, you have to have. Okay, so there was one more. Okay, let me explain one more and then I'll come back. So there is yet another automaton for this, which is this thing. Why should it be the same thing? Like there are some extra states. So I will be calling these circles as states. Okay. Now, if I look at, so this is also going to accept this language. See, whatever this is doing is already there. I mean, this thing is already there. The starting position is here. As long as you are reading an A, you stay here and you accept the word. The moment you read a B, you go to a state, and this is not a double circle, right? So this is called a non-accepting state. Okay, and from here there is no way you can go back here. So once you see a B, no extension of it can end in a good state. Okay, so if I look at BA, so call this, so suppose this I give a name to this state Q1 Q2. So and if I look at BA, I start from Q1, and from Q1, when I see this B, when I process this B, the automaton goes to Q2, right? So I go to Q2. Now at Q2, if I see an A, I remain in Q2. And this Q2 is a non-accepting state. So BA is rejected. Okay. On the other hand, AAA will be accepted for the same reasons. Okay. So let me explain one more example and then we will see. So let's probably take AB star and say this automaton. Okay. So I will draw that. So firstly, so let me take AB star. This is the language epsilon AB, 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 and so on. And the automaton that I drew for it was looking like this. I want to give names to this. I'll call this Q0. A goes to Q1, B, and here if I see a B, or here if I see an A, I go to this Q2, and from there I just do AB, and one of them, this is the double circle here. Okay, and I claim that this picture also represents this language. So how? See, you should think of it like this. So if I take a word in this language and I run that word, on the automaton should end in a accept state, which is Q naught here. Okay, let's take epsilon. My starting position is Q naught, which is already a good state. So epsilon will be ticked. Okay, epsilon will be accepted. Now let's look at AB. So I start from Q naught. This is my starting position. I read an A. I will go to Q1. Now I have to read a B. From Q1, if I read a B, I come to Q0. And Q naught is good. So AB will be ticked. Now once again look at AB, AB. I start with Q naught. I read A, B, A, B. I come back to a good state. So this is ticked and so on. So if I take any number of ABs, I will come back here. On the other hand, suppose I take a word which is not there in this set. Let's take the word B. Okay. The automaton should go to a state which is not accepting. So start from here. When you read a B, you go to Q2, which is not accepting. Okay. For that matter, you read any BA, say. What will happen? From here, this is my starting position given by this arrow. From here, I read a B, I go here, and then I read A, B, A, B. So that's what this says. When this arrow with A comma B, it means that you can either read an A or a B on this edge. Okay. And then finally, after reading all of this, the automaton ends here. Okay. So in some sense, this can be seen as a machine which reads the words and ends in some state. Okay. And if that state is accepting, that word has been processed and accepted. And if that ends in a reject state, the word is rejected. Now you look at the set of all words that are accepted, that will be the language. And in this case, this is the language of this machine. Because the only set of words that can be accepted are of the form A, B star. Okay. Is there some
Sir,
question? Yeah.
single circle is
Correct.
rejecting state
Yes.
at any point.
Yeah. If you
Okay.
reach a, I mean, see, finally you have to read the entire word if possible, and then see where you end up. Okay. And if that end state is a reject state, then you reject the word. See, the other automaton for this was just, let me erase this. So once again, guys, we will see some more examples and then you will get a feel of it. So just be patient a little bit. But yeah, so if I say this is, call this P0, P1, AB. See, in this automaton, again, all these words will be processed and they end in an accept state. But if I take the word BAB, so starting from here, there is no way to read a B. Okay, so the automaton cannot even read the word. Okay, so this word is rejected. Okay, it's like the automaton gets stuck. Okay, so here the automaton is not getting stuck on this, but it ends in a reject state, so it will reject it. In this, it is just getting stuck. Okay, so you anyway get you reject it. Okay, the BAB part I will explain. Someone has asked me to explain again. So if I look at BAB, if I read B, if this when this automaton reads BAB, what happens? It starts from here. The first letter is a B. What will it do? Because from here it can only read an A. So I forgot. It can only read an A. It does not know what to do with a B, so it will immediately reject it. Okay. Whereas here, the automaton knows what to do with a B. It will go to this state. It knows what to do next. It knows what to do next. But then it ends in a state which is not accepting. So it will reject.
So,
Yes.
sir, if it's stuck, like in the example on the right hand side.
This one.
Yes, one. Yes. So, will this be a valid answer because because it's not in the rejection state, but it's getting stuck?
So the automaton is accepting a word only if it is able to process the entire word and end in an accepting state. That is the condition. So this is the definition of it. Like so this picture, when does this picture represent this? So there should be a definition when, and that is intuitively it's like this the picture, this automaton should read the entire word and end in an accept state. Okay,
Means if it's getting stuck, so
it
that
will
is
reject
something
it.
we
Yeah,
can.
you have to reject it. It's not part of its language.
Okay.
Okay, so someone asked for the second expression. Let me just explain that: AB plus AA plus BA, and then we will see some more. Yeah. So AB plus AA plus BA, and this stands for the language AB comma AA comma BA. Okay, now what was the automaton for this that we drew? It started with some state, it read an A, and after that there are two things it can read. It can read a B or an A. So that is succinctly written like this. Okay, so it can read A followed by A followed by B, and accept. The other option is it can read a B followed by an A and accept. So it's like, see, suppose somehow I draw all the strings that can be that are there in the language. This is something like that. This, like I'm drawing AA, AB, BA. Instead of just drawing A, B separately, I can afford to draw it. I mean, I'm succinctly drawing it like this. It gives me the set of all words that are there in the language. But of course, when the language is infinite, I don't want an infinite picture. I want a more succinct picture. That is when we need to give a definition. So all these cycles come into picture. Like here, there were no cycles. Here, there is a cycle to represent that it's AB star. Okay. So in a
Sir,
sorry.
can we go to the previous slide?
Yes.
Here, if we take care of the rejection rules, then we have to take care of all the rejections that we possibly have.
Correct.
Like in this case, ABB or suppose BAB or whatever, whichever things are not included in the set, we have to take care of all those.
Yes.
I mean, if we include at least one, we have to include all those, or
Correct,
we can
correct.
just skip.
No, you're right. So for example, ABB, isn't it rejected by this? Because you go to A and you get stuck because there is, sorry, what was this? ABB. So you do A, you take B, and after that, how do you do B? There is no B here.
Yeah, that's what I'm saying, that if we don't take care of the I mean, if we write an automata where it gets stuck, it's okay, like the second one. But if we take care of if we have to take care of the cases where it will reject with a single circle, then we have to take care of all the things. Like here we have taken care of when it first encounters a B, and then also when it encounters double A or triple A.
Yes.
We cannot just have two and skip the third one. If we
see, no, we have to see. Finally, it has to reject everything that is not there here, either by going to a reject state or by just getting stuck.
For example, in the first automata, if we had not drawn the line from Q1 to Q2, would it be fine?
It will be fine. Yes.
Oh.
Yeah, good question. Yeah, it will be fine. It is yet another automaton. Just that whenever you see an A after an A, you get stuck. Here, it's some sense complete. You know where to go. Okay, but that is also yet another automaton, which is
halfway complete is also allowed.
Yeah.
Okay.
Okay. So yes.
So can we have more than one accepting state in one automata?
We can have. I was about to come to this. Yes.
Oh,
so we will come. Yes. We have to guarantee that the diagram will reject everything that is supposed to be rejected. Okay. So intuitively that is happening here. Okay. But in principle, we have to guarantee that it accepts everything in the set and it rejects everything that is outside. Okay. But we need to formally define what is reject, what is accept, and so on. Right now we are just looking at it informally. Okay, so then we will come to that.
Is
Then
there
we can.
any advantage of the formula which is on the LHS over the one which is on the RHS?
You mean this versus this?
No, yes, sir.
Ha. So the regular expression versus this.
No, sir. This expression versus the one short one on the right hand side.
You mean this versus this?
Yes, sir.
I mean, there is no advantage, anything like, it's just they represent the same object. Okay, here there are fewer states. Okay, so if you are implementing something, I mean, anyway, it's not there is no advantage as such. Here it is kind of more meaningful because you know what to do at every letter. Here you are just getting stuck, that's all. But both of them represent the same.
We can consider both as equivalent.
Yes. There is no no difference.
Okay.
In the thing that they represent. Okay. Okay. So you get some idea of what automata are. Okay. So why don't you try these exercises? Okay. And then slowly we will build automata for each of them, and then you will get a feeling of what automata are. Okay. So I'll just give some time for
So we should consider the alphabet as A and B, right?
Yes, yes, yeah.
Sir,
Yes, yeah.
can there be two start states?
For the moment, no. Okay, so try to not have it. So in next class we will have two start states. Okay, so which example are you at?
Sir, 1.8 actually.
Yeah, I guess. Okay, no, try to draw it without two start states.
Okay, sir.
Okay, so let me start explaining, and then maybe so let me start with A sigma star. Okay, so A sigma star. Okay, so you have to read an A, and after that you can read any letter. Okay, so what will my automaton do? It will start at Q0. It will read an A and go to, so now I'm giving terminology. Okay, it will go to a state Q1, and at Q1 it can read A or B. Okay, so this is the, so this one accepts all words that start with an A. Okay, if I see a B, there is no, I mean, I can always put a B and go to a state where I do, I mean, from where I can never accept. Okay, that's fine. Or I just stop it here. Okay, so I'll just mark some terminology here. So these circles are called states. Okay, these lines are called transitions. Okay, this arrow on one state is called the initial, it denotes the initial state. Okay, now this letter on this transition is called an action. You can You can sometimes you can call it an action or a letter, doesn't matter. It's the letter on the transition or the action on the transition. Okay. And then what is this notation? This stands for a short form for two transitions. From Q1, it stands for A, B. Okay. So states, circles are states. So I forgot that. And the double circle stands for accept states, also called final states. Okay. Now, yeah, let's look at the second thing, A sigma star B. Okay, it should start with A and end with B. Okay. So I start with A, then I can read A or B. But, okay, no, sorry. Yeah. As long as I keep reading an A, I stay here. If I read a B, maybe my word has ended. So I have to go to an accept state. But then if not, if I'm still reading a B, it is okay. But if I'm reading an A, I have to go back here. So yeah, this is a slightly tricky thing, but this is the automaton. Like, so I start from here. So let's do an example. Like, for example, A, B, A, B, say. This has to be accepted. Okay. What will the automaton do? So I give names Q0, Q1, Q2. Okay. It will start at Q0, read this A and go to Q1. Okay. At Q1, it will read a B and go to Q2. Okay. Now it's at Q2 and now it has to process an A. It will come back to Q1. Okay. And then again it sees a B and goes to Q2. And my Q2 is an accepting state. So this word will be accepted. Okay. Now let us look at another word, say A, B, A. Okay. Now how does it how does it work? It starts at Q0, reads an A, go to Q1. From Q1, if it sees an A, it again stays at Q1. And Q1 at B, it goes to Q2. Q2 on A, it goes to Q1, and Q1 is not an accept state. So this will be rejected. Okay. Is this fine?
So we could also have a double transition on Q1, and then we could move to an accepting state if we get a B, and a rejecting state if we get an A.
Wait. Sorry. Is this what you had in mind? Like, wait. I think.
But sir, I think that will be NFA.
So yeah. So NFA I wanted to do next class, but so yeah. Wait. No. So what you have in mind? You wanted to do this A, B, B. Is this what you had in mind?
Yes, sir. So Q2 is an accepting state.
Sorry. Yeah. This is a finite automaton, but
and also another state from this middle one. Also transition from the middle one. If it gets an A, then it ends.
Why?
Like if the last letter is an A, then it.
Oh, you mean from Q2 or from Q1?
No, from Q1.
Let's stick to this for the moment. Okay. So
okay.
Yeah. Now, see, here, see what happens if I see A, B, okay, let's see. Suppose I have something like this. Okay. Now, see, I read an A, and when I read a B, there are two choices. Okay. But yeah, of course, you will choose to do this because after doing this, I cannot read anymore. So what you will do this, then you will do A, and then you will do B. See, this is slightly different from here because for every word, there is only one way of reading it. Okay. So that is why this is called a deterministic finite automaton. There is only one way of reading the word. We will see objects like this in the next class. Okay, so bear with me until then. So it's not wrong for this example. Okay, in this example, this is correct.
Okay, sir. Okay, sir.
Okay, but let's not. So here, let's not look at it for the moment. Okay, so the condition that we want to impose so far, we have not explicitly seen, is that from every state, okay, let me draw it. So in a deterministic, why are we calling it deterministic finite automaton? So from every state on a letter, there is a deterministic choice. You do not have two choices. So no choice is also fine. Like if I have, for example, Q naught A B is fine, because at Q naught on an A, I have this. At Q naught on a B, I'm just stuck. Okay. At Q1 on an A, I'm stuck. From Q1 on a B, I come here. Okay. So later we will see machines which will be called non-deterministic finite automata, where you can have multiple choices. So like we had in the previous case. Oops. Okay. So let's not worry about that later, because multiple choices at a state on a letter. Okay. So for the moment, let's assume that we have a single choice at every state. Okay. So here, for example, there was a single choice A. If I read a B, I just have only one choice. I go here. If I read an A, I go only here. From here, if I read a B, it's like this, and on an A, it's like this. So from here, you can add a dead state. Okay, that's fine. But even otherwise, it's okay, because if you start with a B, so if I have a letter which is say BA, okay, my automaton, what happens? It starts at Q0. It cannot read the word. It just gets stuck. Okay, so it will reject it. Okay. Fine. So what about 1.3? So sigma star A B sigma star. Okay. Sorry. So the next example was sigma star A B sigma star. Okay. So all these are okay. So what do we do? Suppose I read an A and a B, I go here, I read an A, I stay here, okay, and I come here, I read A, okay. See, you have to accept the moment you see an AB, okay. So when I first see an A, I am waiting for my next B. Until then, I keep reading A and stay in the same state. So in some sense, the state is recording the fact that the last seen input was A. The last seen letter was A, and I'm waiting for a B. And the moment I see a B, I go to the state, and here I can read anything. And yeah, sorry, there is more. Yeah. So initially, if you keep reading B's, you stay here. Okay. The first time you read an A, you go here and wait till you see a B. Okay. So it's like if I have a word, say B, B, A, B, A, B, say. The first time I see an A, I jump to this, what is this? Let's call Q0, Q1, Q2. Q0, I keep staying at Q0. The first time I see an A, I go to Q1. I stay in Q1 till I keep reading A's. The moment I see a B, I go to Q2. And then I stay at Q2 to mark the fact that I have seen AB. Okay. So is this
in the last circle,
huh.
is it this deterministic?
It is deterministic. So why not? See, from Q2, if you see an A, where do you go?
Either A or B.
No. So that's what. So this, no. So this is just standing for two transitions. So from Q2 on an A, there is a single choice. From Q2 on a B, there is a single choice. Okay. If I had Q2 on an A, I just kept going randomly, say Q3 and Q4. This would have been a problem. This A. In the sense, this is not deterministic. Is that fine?
Okay. Yes, sir. Yes, sir.
Okay. So let me now actually formally define it before I go through the rest of the examples. Let me actually formally sorry.
Sir, for 1 second, could we go back to the previous example 1.2?
1.2 was this thing. This thing, right? A sigma star B.
Yes, here I wanted to know if the transition from Q0, then we are taking A, is that redundant? Could we start from Q1 and take it to A over the loop?
See, okay, very good question. See, what happens in that case? Okay, suppose you start from here. Okay, now there is no guarantee that you see an A. You can also read, say, just B.
Oh, okay, yes, got it.
Yeah,
Got it.
yeah, but yeah, good question.
So because in the next one, we directly started it from B, we took a B and A, so I was wondering if it was redundant, but now it's cleared.
Yeah, okay.
Yeah.
Okay, so maybe I'll just do one more example and then I will start defining it formally because now we have had enough practice. So let me do even number of A's. Okay, so even number of A's. Sorry. See, now my automaton should count modulo 2 since. Okay, so what does it do? In order to know whether it's even or odd, I mean, I just need to remember two states, whether so far the number of A's that has been seen is even or odd. Okay, so as long as I see no A's, I have to accept because it's even. 0 A's is even. when I'm here, maybe I'll call this, so I'll call this state Q even, Q odd. These are the two states. And this is my initial state. Okay. When I am at an even state, so far I've seen even number of A's, and if I see a B, the number of A's is not changing. So I stay at Q even. Similarly, from Q odd, if I see a B, the number of A's is not changing, so I stay here. But from Q even, if I see an A, it means that now the number of A's that I've seen so far is becoming odd. Okay. When I was in this state, I had seen an even number of A's, and from that, I am seeing another A. So far, the number of A's that I've seen is odd. And from here, I have to come like this. So try to run, say if I want B, A, B, A. Okay, it has even number of A's. So you start with Q even, you stay at Q even, then you read an A and go to Q odd. So far you have seen one A, so it's an odd number. Then you stay in Q odd only, because so far you have seen one A, and then you see another A, you come to Q even. Okay, I can extend this, say A. Okay, but from Q even I see one more A, so there are three A's, but I track that it's odd. Then again I go to Q even, I go to Q odd, it will be rejected. Okay, any do you get this? Any questions? Okay, fine. So let me actually define deterministic finite automata, syntax semantics. Okay.
Excuse me, sir.
Yes.
So what if we don't write two B's in the last example? Would it be fine?
See, the problem is, so you mean we don't put this and this?
Yes.
See, then how would you accept this? Okay, how do you accept, say, the word BAA? It will get stuck, no? So at Q even, if you don't put a B, it will get stuck.
Okay.
So deterministic finite automata. What are these objects? Is there a question?
Sir,
yeah.
So how are these like used in the the practical field? Do we design circuits based on these things, or do we write codes for these things?
So see, these are all what do you call abstract objects representing some kind of a computation. Okay. See, we will see later that they will be used for this regular expression search on a string. So that is one way of using it. Okay. So when you want to match given a string and a regular expression, trying to see if there is a pattern matching that regular expression in that string, you can use these kind of objects. Okay. Compilers use these kind of for parsing. They use internally automata for parsing as a representation of what it has read. Okay.
So essentially, we are like going to use these as algorithms, right?
Yeah.
Okay. Thank you, sir.
These can be used as algorithms. There is a second way of using it, which is like models for real things. Okay.
As in
you can so these are all like finite state machines. Okay, so circuits can be represented using automata. Some other I don't know, some other processes, biological processes, certain processes can be represented using automata. Some kind of I don't know, the very canonical example is an ATM machine. The computation that goes on in an ATM machine can be represented as an automaton. Okay, it's like a finite, so essentially, here the state had a meaning, Q even. Here we just wrote Q0. Okay, but maybe there are some variables and stuff, and then that state will actually have some other meaning. Okay, So these can act as models of other real life things. So you Google for it. Okay.
So essentially, these are like processes for like describe. I mean, these are tools for describing certain processes, right?
Yes. Finite state processes. Okay.
Okay.
Good. Yeah. Anyway, so let's come back to deterministic finite automata syntax. So by syntax, how do you describe the automata? So this we have seen. So there is a finite set of states. Okay. So in this case, the set Q was Q even comma Q odd. In this case, the set Q was Q naught, Q1, Q2. Okay. Then a designated initial state and initial state. Okay. So of course, I'm assuming that we have a finite alphabet. Okay. And then there is a transition function. So that means what? What does this delta do? It maps. That means what? So delta of Q even comma A gives me Q odd. Delta of Q odd comma B gives me Q odd. So it's a transition function. That is, given a state and a letter, to which transition I go. To which state do I go? Okay. Now, if this is this can either be a complete function or a partial function. Okay. In the partial function, so for example, where was it? This is complete. In this case, it's a partial function because at Q naught on a B, I'm not saying what to do. But Q naught on an A, I'm saying what to do. Okay. Yeah. And then finally, a set of accepting states. So this is the formal definition of how an automaton looks like. So this picture is very intuitive, but sometimes it might be, there are several questions. No, what is this? What is that? Can I have two arrows and things like this? So now this formal definition fixes all these things. You can have only one initial arrow. Okay. From a state on an A, you can only go to one state. You cannot have several things because this is a transition function going from Q cross sigma to Q. Okay, so that fixes it, and so on. A set of accepting states. You can have several. There can be multiple accepting states. Exactly. Okay, so far we have not seen. So think of a language which needs multiple accepting states. Just think about it. Okay, so but in the meantime, let me finish the semantics because there's only 6 more minutes left, and I'll continue from this point in the next class. Okay, so semantics of DFA. So we will shortly call it DFA. Okay. By semantics, what do we mean? So what is the language accepted by a DFA? What is the language by a given DFA? By a DFA. Okay, so let's say the DFA is Q naught sigma delta F. Okay, so here is where we will use the intuition that we have developed. We have to first run the DFA on a given word, and the language of a DFA is the set of all words that it accepts. Okay, so for this we need to define what is called run of a DFA A on a word W. Okay, this needs to be defined carefully. Okay, so suppose W is of the form W1, W2, W3 till some Wn. So a run of a DFA is a marking of states Q0, Q1, Q2, so on till Qn, such that Q0, sorry, Qi, Wi plus 1, Qi plus 1 is a transition. Okay, so example here. So this is the word, this is the run of this DFA on this word. It's the intuitive meaning. When you read the word, what are the intermediate states that you encounter? Okay. Now, so please stop me at any point. Okay. Like if you don't understand, of course, I mean, yeah. So now a word, okay, let me say that what is an accepting run? Okay. A run is accepting if the final state, I mean, first of all, is in F. W1, W2 are individual letters of the alphabet, yes. Yeah. Yeah, they are not. So W, yeah, you're right. Yes, the W1 is just a letter. Now a run is accepting if the final state, if this has to is in F. Okay. So by the way, in the definition of a run, you have to see this entire word. You cannot stop here. Okay. A run itself has to see the entire word. Okay. Now, let me, if in a complete DFA, what is a complete DFA? The transition function is complete. Okay. Now in a partial DFA, it's not complete. Okay. Now, given a word W, a DFA either has a run or not, because it may get stuck in between, because in case the transition function is partial. So I will stop this formal jargon in a couple of minutes, so bear with me. Okay. Now, the last thing is language of a DFA, which is the final thing that we want. That is the set of words that are accepted by the DFA. Now then, what does it mean to say the word is accepted? A word W is accepted by DFA A if A has an accepting run. On W. So either, see what can happen, either the word can, the run can get stuck, or the run can, there is a full run which ends in an accepting state, or there is a full run which ends in a reject state. Okay. The only time when you accept the word is it has to see the entire word and end in an accept state. Okay. Now you look at the set of all words that are accepted, that will be the language of the DFA. So now that you have seen this, you go back and look at the examples that we saw and see that it will match with this formal definition. Okay, so it's actually already time. So I'll stop here. I will just leave you with an exercise. Okay, so of course this is already there. The rest of these things are already there. Okay, you try this out. There is another exercise that I wanted to give, which is not. So this will be an exercise. So what is the, so this is a reverse. So I give you automata, find the languages. Okay, so I just leave it as an exercise. I will do it in the next class. So I'll just summarize now. So what is the, we have looked at DFA as a representation for languages. So we have seen some syntax. What is the semantics means, what is the language of a DFA, and largely examples is what we have seen. So please go through those examples, see that they match with the definition. If you don't understand the definition, just try to, I've given the reference so you can take a look at it. Okay, now and then you keep keep matching the examples and the language and the formal semantics. Okay, so we will do some more examples of DFA in the next class, and then bring in this idea of this non-deterministic finite automata in the next class. All will lead to converting regular expressions to one of these formalisms. Okay, so I will stop here and I will stay back for questions if you have any. So tomorrow there will be a quiz. So I'm sorry I have not corrected your quiz 1 answer sheets, and I don't think it will happen by tomorrow. I will try to give both the answer sheets by the end of this week. Okay, so yeah, apart from that, quiz 2, as I said, it's between 2 to 5. So I will upload it around say 1:55 or something like that. Okay, yeah. Okay, so the class is over. You can feel free to leave. And if you have any questions, you let me know.
Sir, in case of accepting run, it is the set of the states, and if the final state is in the set of the final states, then then we just said that.
Correct. Yes. Correct.
Okay. Okay, so that was my question. Thank you.
So there's a question. It's a typical Prashun Agarwal question, which is all questions in quiz needs to be solved using natural deductions. No, I actually said in the last class, I think, and it's not needed. So there are, if for these puzzles, you don't need to use natural deductions. Okay. Well, of course, there'll be specific sequence to solve that you will have to use natural deductions. Yes. Yeah. So you can just give your own argument. Yeah.
Sir, I have a doubt in sequent. Sir,
yeah.
So in lecture 7, there was a problem where P and Q imply R, from where I have to show P implies Q implies R. Okay, there in that problem, we assume P, then Q, and then we solve the problem. And my question is that why we don't assume not P? In not P, it will be a trivial one and we can show that, but why we don't assume that?
No. See, we have to use the rules, no? So if you use not P, how do you derive P implies Q implies R?
From not P, actually not P will be, from not P we can derive anything. It will, not P will be 1, then P will be 0. So
No, you're still using truth table. No. See, I understand that from the truth table, I agree. But from the rules that we have given, like the implies introduction, implies elimination, there are some set of, like, I don't know, some 7-8 rules, no? You have to use only those rules to get what we want. See, that is the point of this exercise.
So we don't miss the point not P, actually. we have P and not P.
Wait. I
So,
think I don't
sorry, P or
understand.
not P.
Wait. Let me try to understand what you're trying to say. See, what was the sequent? The sequent is P
P
implies
and
Q. Sorry, P implies R, Q implies R. Is it?
P implies Q implies R. Bracket Q implies R.
This is the premise?
No. Premise is P and Q implies
okay.
R.
P and Q implies R. And I want to show P implies
Q implies R.
I want to derive.
Yeah.
Yeah. Okay. So what is your derivation?
Premise is P and Q implies R. Then we assume P, and then
No.
Q.
That is what we. That's how we did in class. But what is the thing with not P that you are suggesting?
Suppose we assume not P.
Okay, let's do it. Not P assumption.
And then what I actually told that if not P, then P will be 0. So we can derive not P.
I mean, tell me what is the next statement I write here based on what we did.
And then assume Q.
Assume Q. Okay.
And then P, not P, actually P and Q will be 0 then. So actually I stuck
How
in
do you
this.
write that here?
Actually I stuck in this problem.
No, so the thing is you are doing it based on the truth table. Okay. See, the entire point of this exercise was to use the certain fixed rules that we have in deriving what we want. So you cannot use the truth table. See, I am not asking you to show in words or in truth table that if this is whenever for all valuations of PQR, whenever this is 1, show that this is 1 also. I'm not saying that. Use the natural deduction rules to derive this sequent. Okay. See, whatever you say is correct, but it's not what we have asked to do. You see? Do you get it?
Yes, yes.
Okay, good.
Excuse me, sir.
Yes.
Sir, I want to ask that in the questions which we were doing, the initial state, okay? So if we put a condition on the initial state, okay? And if it does not satisfy that, so will that imply that it will not move forward or
no, sorry. I missed your question. Yeah.
Like, okay, my particular doubt is I was trying to solve B star A star, okay?
Okay.
So what I did was my initial state is an accepting state, and that will be recursively on B, because if it till the time it will see B, it will keep going in that state, and if it sees A, then it will go in another acceptance state, and if it sees B, then it will go in the rejection state again.
Correct. Yes, this is fine.
Right. So my first state is if it sees B, so it remains in that state. But what if I have a word like AA? Okay. So this is a valid word as per this. This is a valid word. So will this go in state Q1 or will this reject it?
Why won't it go to Q1?
Because
starting from Q0, when you see an A, where do you go?
Okay. So, okay.
Yeah.
Yeah, I got it.
Okay.
Okay.
Yeah. So there's a question on the chat. How many questions can we expect for tomorrow's quiz? I don't know because I am yet to prepare the question paper. So I will see. But see, I think you guys have done enough work on this. Like there'll be some questions on puzzles and then some questions on sequence. Yeah.
So I have a doubt. One that is, if there is no premises and we have to derive that conclusion, so is there any? Actually, we are getting a lot of confusion. What to assume and what to not assume. Is there any specific rule? Okay, if premises is not there, you can assume like this.
See, sometimes you can use LEM. This, I mean, if it works, but typically you assume the not of that formula that you want to show and try to get a contradiction.
Okay.
Then you can show that, this is one rule of thumb. Yeah, this may work several times. Or second, you can use LEM sometimes, because that doesn't need any premise. It's always true.
Okay.
You can use a convenient LEM that serves your purpose. I mean, it doesn't have to be P or not P. It can be like P and Q or not of P and Q. These kind of things. So.
Okay. Thank you.
Yeah. Any other questions? Okay, so if there are no other questions, so we can stop here. All the best for tomorrow's quiz. Then
Thank you,
we'll
sir.
meet on Thursday.
Thank you, sir.
Yeah. Bye.
Bye.
Thank you, sir.
Thank you, sir.
Yeah.
Happy Republic Day.
Thank you. Yeah. Yeah. Okay. Bye then. Yeah.